All right, we're back after a little disruption there. This is chapter 15, number 58 that we're working on. And we just found out that the luminosity of a star is proportional to the square of its radius times the fourth power of its temperature. Now, looking over here, we can start the problem and we can play a little trickery to make this easier for us. Okay, in chapter 15, problem 58, we're given the star Sirius, and we're told it has a luminosity of 26 times that of the sun, and a photosphere temperature of 9,400 Kelvin. We could use this version of the formula if we convert the luminosity to watts. There's a part of me that does want to do that. There's another part of me that thinks we could be smarter here. If you imagine dividing this formula for Sirius and dividing it by the same formula for the sun, 4 pi's and the Stefan-Boltzmann constant would cancel out. And then what you would get is the luminosity of the star would be the radius squared times the temperature to the fourth power, a simpler version, if you use these units. For the luminosity, you use solar luminosity units. For the radius, solar radii. And for the temperature, you'd have to use solar temperature units, where this was how many times greater or less the star was than the photosphere temperature of the sun. Does anyone remember what the temperature of the sun is? Begins with 5. It's a number of order 1,000. Not 1,000. 5,800 units. Wow, not bad. I'm impressed. Nice. 5,800 Kelvin. Okay. So what about our temperature here? We have the luminosity in solar luminosity units. Let's see if we convert our temperature to solar temperatures. 9,400 Kelvin. Let's do dimensional analysis from Kelvin to solar temperature units. One solar temperature is 5,800 Kelvin. Punch that in and give me 2 sig figs. Punch it correct. Punch it correct, please. Thank you for my ketchup packets, Noah. What'd you get?
Ketchup packets. That's what I got. 1.6.
1.6 solar temperatures, or whatever you want to call it.
Or ketchup packets.
1.6 ketchup packets. Actually, I believe, oh, I don't want to touch that. Okay. All right, so if I solve for radius, I get the radius is the square root of L over T to the fourth power. Now, in solar luminosities, it's 26. In solar temperatures, it's 1.6 times 10 to the power 4. Okay? So, let's show the group how to do this.
All right, let's take out the ketchup packet.
Let's get a little nutty here. All right. We'll do 26 divided by 1.6. Hit the x to the y key, raised to the power of 4 equals, you should see 3.97. Now we have to square root. So shift, square root. What'd you guys get?
Got me going, dude. You got me going.
I want to turn this around to show them what a class comm looks like, but I don't want the video to stop again.
I'm a Scrooge.
All right. Can you give me a number?
Yes, Tom.
These are the looks of students losing their shit, okay?
Oh, I'm offended. I'm offended. Am I hitting shift in the square root, or am I hitting square root right away?
This is what the kids are using these days.
Yeah, that's a flap of a kitchen packet. It was over
All right, look, are we ready to learn now? All right.
Well, hold on. Hold the phone. Because I asked, am I hitting shift then that, or am I just hitting?
You have to hit equals, then shift. So you do 26, divide by,
So then I got 0.04.
no, 26, just clear it out and do what I'm telling you to do. All right, you ready? 26, hit the divide key. Now do 1.6. Now we need to raise that to the power of 4. So I'm going to hit this button here, the raise to the power of 4, and then you hit equals. And you should see a number that's close to 4. Now we're going to hit shift and square root. What did you get?
What did you get?
Well, what did you get?
What did you get?
Well, I don't know if I'm really telling you.
I'm telling you, I got 0.4.
That's not
I
right.
mean, 0.04.
2.
Yeah.
2 what, though? I'll help you know.
Like WPH.
2 what? Solar radii. All right, well, they copy. Let's take a look. Clear it out. Divided by 26, divided by 1.6, raise to the power of 4. No, that's ESP, that's raise to the power of 4 equals. Now shift through. What we had there was a failure to use your power key.
And you forgot your pencil packet.
Clearly. Okay, that takes care of 58. Moving on.
Wow.
Okay, chapter 16, number 50. This is about a newborn star cluster.
Honestly, I'm very disappointed that nobody else from the class is in.
Well, we'll see them soon enough. Okay. Suppose a new star cluster is born with 1 spectral type O star, 10 spectral type A's, 100 spectral type G's, and 1,000 spectral type M stars. What stellar type dominates the light output from the cluster? Also, what would the color of the star cluster be if you observed it from a far distance so that you just saw a big smush of light and not individual stars? Okay, let's make a little picture here of what's going on. So, here on the HR diagram, we can see our different spectral types, right? O stars are blue, A stars are white, G stars are yellow, and M stars are red. So, we use some appropriate colors. We have one O star. That looks like 10, so I want to fix this. So we'll say one O type. Right? We have 10 A types. Now, spectral type G are yellow, but I'm going to use green for spectral type G. I'm sorry, what was it, 100 G types? Right? And yeah, 100 Gs and 1,000 M stars. So this is what our star cluster looks like. Maybe it would be best to tabulate this in a sort of table form, okay? So let's go over here and let's do this as a table. I'll have a column for spectral type, a column for the number, a column for the luminosity of a single star, and then a column for the total luminosity of the stars. So this is spectral type. This is the number. This is the luminosity per star. And this is the total luminosity. So, using some creative colors, I have an O type, of which there's one, an A type, of which there's 10, a G type, of which there's 100, and an M, for which there's 1,000. All right, students. It's time to use our HR diagram to figure out the relative luminosities. So I don't cancel my video again. If you guys can see this here, I don't know how, let me back it up. Okay, let's use it here. So let's start with the O type. Tracing the O up, we hit the main sequence, and we go over. What do we have for a luminosity? You can't read that?
Wrong line. Is that 9?
That's 10 to the power of 6.
Okay.
Solar luminosity units. How about a spectral type A? We go up to the main sequence, and then over.
I think it's just 10.
I think it's more than that.
Or 10 to the second.
Yeah, it's one of those two. I think 10 to the second works a little better. Okay? It's a bit of a judgment call. How about a G-type? You're supposed to know what a spectral type G does, right? The sun is a spectral type G. So it's just one solar luminosity, just like the sun, right? How about an N-type?
What was it again?
Spectral type M.
I don't know where that is.
Same color as ketchup packets.
Okay. Same color as a ketchup
10
packet.
to the negative fourth? Or negative 3?
Yeah, I think -3. I'd say -3 does it.
Same color as ketchup packet.
Okay. Can you guys tell me my total luminosity for the blue star? Oh, shoot, sorry. Total luminosity for the blue star, what do we got? Don't think too hard about this, guys, just multiply it. One times 10 to the 6 solar luminosity units, yeah. It's 1,000,000 times that of the sun. How about for the A-type? Sorry? 10 to the 3rd, which is what? Yeah. 1,000 times that of the sun. Okay, how about the spectral type Gs? How about the spectral type Ms? Yeah. This is 10 to the 3rd, right? 10 to the 3 times 10 to the minus 3 is 10 to the power of 0, or 1 solar luminosity unit. Cool. So which color and which type of star dominates the cluster? Yeah. So the way this works is the blue stars dominates the light output and the color of the cluster. And so this cluster of blue stars, well, in this case there's only one, but in general, the blue stars will outshine all the other stars. And these types of clusters are called open clusters in astronomy. Open clusters, for example, would be like the Pleiades. Is it I before E or?
There's a lot of questions.
Huh?
There's a lot of
Yeah, I just couldn't remember if it's. Okay, well, I think that's how you spell Pleiades. I'm not sure. No, it's okay. All right. One more to go.
Oh, yeah.
The last problem is about binary star orbits. And this is sort of an important rule that we're going to use in our lecture, and we're also going to use this in our labs today. So 59 is about a binary star orbit, one that includes something called a brown dwarf. A brown dwarf is a failed star, something sort of like Jupiter, that didn't have enough mass to turn on nuclear fusion. Whenever you have a binary star, you usually have a high mass star, capital N, and then oftentimes there's a lower mass star, little m. And the lower mass star kind of goes whipping around the high mass star. Because the little guy has less mass than the big guy, it will end up having the greater velocity.
And there's a famous rule for binary stars that goes like this. The ratio of the masses, say the big guy to the little guy, will be the inverse ratio of their velocities in the binary star system. So if massive star is 10 times greater than the little guy, its velocity will be 1/10 as much, because it doesn't get whipped around as much in the binary orbit. That's a wicked important rule. The ratio of the masses is the inverse ratio of their velocities. All right. With that in mind, let's play the game. This one's called Mass of a Brown Dwarf. Suppose you observe a binary system containing a main sequence star and a brown dwarf. The orbital period of the system is 1 year, and the average separation, the semi-major axis, is 1 AU. You then measure the Doppler shifts of the spectral lines from the main sequence star and the brown dwarf, finding that the orbital speed of the brown dwarf is 20 times that of the main sequence star. How massive is the brown dwarf? Get ready for this. It's going to be cray. Okay. So if this is A, the radius of orbit, we have a radius of orbit of 1 AU, and we have a period of 1 year. And what that tells me is that if I use Newton's version of Kepler's third law, the so-called Kitty edition, I can solve for the total mass of the system, which is the mass of the normal star plus the mass of the brown dwarf. And if you use Keplerian units, it's simply a cubed over p squared, where a must be measured in AU, p must be measured in years, and the masses of the two stars will come out in solar mass units. Well, this problem couldn't be any dumber, right? We have 1 AU cubed over 1 year squared, giving us a total mass of 1 solar mass unit. But now we want to try to figure out the mass of the brown dwarf. What do we know? We know that the mass of the star divided by the mass of the brown dwarf should be equal to the velocity of the brown dwarf over the velocity of the star. That's the binary star rule. Sweet. So what's that equal to? What's that equal to? Do you guys remember what the givens were? What was the given? It says, measuring the Doppler shifted spectral lines, you find that the orbital speed of the brown dwarf in the system is 20 times that of the main sequence star. So what do I do? Did you understand those words?
the ratio of the brown dwarf to the star's velocity is 20. That's all it said, right? Let's see. That means if the mass of the star divided by the mass of the brown dwarf is 20, then the mass of the star is 20 times greater than the mass of the brown dwarf. Right? You also know that one solar mass is the mass of the star plus the mass of the brown dwarf. What do you do now, guys? Do you know what to do? Did y'all take like Algebra 1 and shit? Because you know what that reminds me of? That reminds me of 2 equations and 2 unknowns, right? That's a solvable system. Right? Well, let's go up here. See what we're trying to do. Okay. You guys seem a little confused. So I have the mass of the star is 20 times the mass of the brown dwarf. I have the mass of the star plus the mass of the brown dwarf is 1 solar mass. Does anyone know how to do this? Huh?
Didn't you put in the mass of the star, the 20 mass of the brown dwarf,
20 mass of brown dwarf.
plus the mass of the brown dwarf?
So what do I do next? This is the critical step. Huh?
You would have to do the mass of the brown dwarf by itself, so you would have to divide it.
No, you don't want to do that. You can't do that.
Minus each side.
No. There's 2 terms here, guys.
You just combine them.
You have to use what my friend Todd calls clever forms of 1, right?
So it's 1.
That's right, because it's 20 brown dwarf masses plus 1 black brown, so it's 21 mass of brown dwarfs is 1.0 solar masses, and therefore the mass of the brown dwarf is 1/21 of a solar mass. What does that give you? 1 over 20%. 1/20th is like 5%, right? I think, right?
No.
Yeah. Right?
Yeah.
So this is basically 5% of the solar mass unit. That's our answer. That implies the mass of the star is like 95% of the mass of the star. But this is our answer. This is the mass of the brown dwarf. Okay, I hope you enjoyed homework, special homework 7.5. You're now done. Don't forget to try your ketchup packets, okay, before you leave. Do you have an announcement, Noah?
Show up to fucking school.